This is an important section, and actually it's two sections combined together, but we're going to go over 5.6 today and finish 5.9 the next day. But two sections are closely related. That's the reason I put them on the same outline. So we're going to start from the same basic questions that we always did in this chapter. We're interested in finding the area under the function f of x on some interval from a to b. So hopefully your graph looks a little better than mine. So we know that in order to find the area, we've seen it before, we need to find the definite integral from a to b of f of x dx. And the fundamental theorem of calculus is going to tell us how to do it exactly. So from this point on, we don't need to go to Riemann sums all the time to approximate this area. So if we're working with continuous function f of x, so function f of x has to be continuous. And then if we know that big f of x is an antiderivative of small f of x, then the integral from a to b of small f of x dx is equal, and we're going to do it as two-step process. We're going to write the theorem the way we're going to use it. So first, we're going to find antiderivative. We're going to keep in mind that we're working on the interval from a to b. And then all we need to do is to plug the upper limit into the value of the function minus f of a bottom limit. Please realize that we didn't add plus c when we found antiderivative, and I will show you on the first example why it's not needed. So we're ready to look at the first example. So we're looking for the area between the function 3x squared plus 1 x-axis on the interval from 0 to 2. And every time when we're talking about the area, I'm going to sketch the graph. I want to make sure that I realize that the graph is above the x-axis, and I realize what area are we dealing with. Because we don't need a perfect graph, just a sketch. So this is 3x squared plus 1 on the interval from 0 to 2. So that's the area we're looking for. So we know that we're going to set up the integral from 0 to 2 of 3x squared plus 1, I'm going to parentheses inside dx. So first, integrate, find antiderivative. So it's going to be x cubed over 3, so it's going to be x cubed plus x. Now I'm going to put plus c at this point on the interval from 0 to 2. Now we're going to plug 2 into our antiderivative, so parentheses, it's going to be 2 cubed plus 2 plus some value c minus, plug in 0, so 0 cubed plus 0 plus c. I hope you realize that c will always cancel, that we really don't need to put plus c. It's not necessary. It's actually silly in a way. And by calculating that value, 2 cubed is 8 plus 2, the final answer is 10. So the area under this parabola on the interval from 0 to 2 is exactly 10 units. So the next example is just an integral, so we don't need to sketch. 5 is the coefficient. We're going to keep 5 outside. Right, so equal. Integral of cosine is sine x on the interval from 0 to pi over 2. So I'm going to keep the coefficient outside. I don't want to deal with too many numbers. Now sine of pi over 2 is actually equal to 1 minus sine of 0, which is 0. So the integral is equal to 5. All right, so let's look at two more examples. I hope you all realized that you had to turn the page. So this is just an integral, right? So the integral of x squared is x cubed over 3. So we're looking at 7 over 3 x cubed plus integral of x is x squared over 2, so 4 over 2 is 2x squared, plus antiderivative of 10 is 10x on the interval from -3 to 0. So the first number that we plug in is 0. Every term has an x, so that's going to be a 0 minus. Now plug in -3. That might take some room, right? I should have probably went to another line. So 7 over 3 times -3 cubed, -27, plus 2 times -3 cubed, 2 times 9, minus 30. Close parenthesis, plug all of that into your calculators if needed. So we're actually looking at 63 minus 18 plus 30, which is equal to 75. Remember, you can find the value of your definite integrals by using your calculators. Under Math 9, you have a function which is basically a definite integral. So some of you who have the old version, I can help you the next class to do it. Try to do it by hand and only use your calculators to check your work. All right, one more example. The function is 1 over x, and now we're talking about the area, so let's sketch the region. This is the graph of 1 over x on the interval from 1 to 5. So that's the area that we're going to be looking for. So we're going to set up the integral from 1 to 5 of 1 over x dx. We remember that integral of 1 over x is ln of x on the interval from 1 to 5. So plugging 5, it's ln of 5, minus plugging 1, it's ln of 1. Remember, ln of 1 is 0. So ln of 5 is an exact area under this function on the interval from 1 to 5. All right, the next theorem basically has a lot of applications, and all it tells you that if you're going to be integrating the rate of change, you're going to get your original function back, and then plugging the top limit minus the bottom is going to tell you the change in the values of the function, how your function have increased or decreased during that time interval. So let's try to look at the next example. So the area of the oil spill is increasing at a rate of 25 feet squared per second, t seconds after the spill. Between times t equals 2 and t equals 4, the area of the spill increased by what amount? So we need to get back to the function, so we're going to integrate the rate of change, which is 25t dt, on the interval from 2 to 4. All right, 25 is just a coefficient. Integral of t is t squared over 2. So the integral is going to be, antiderivative is going to be equal to 25 over 2 t squared on the interval from 2 to 4. So keeping the coefficient outside, 25 over 2, and then inside parentheses 4 squared, 16 minus 2 squared, which is 4. So we're looking at 25 over 2 times 12, right? So 12 goes into 12 6 times, so 150. So the area of the spill is going to increase by 150 square feet. All right, good luck on your homework. Please come back with the questions and we will finish this outline next class.